All right, so the last section in Chapter 8 is going to be 8.5, which goes over 3 theorems that involve proportions. So the first one is called the side splitter theorem, and it says that if you have a line that is parallel to one side of a triangle and intersects the two sides, so B intersects the two sides and E intersects the two sides, it divides those sides proportionally. It is splitting the sides. That is why it is called side splitter theorem. So if BE is parallel to CD, then we can make a ratio of that, or a proportion out of it, that says AB, so this guy over this guy, equals its matching part on the other side. So AE over ED. All right, it doesn't always just have to be one line. This can be expanded further into 3 or more parallel lines. So in this case, we have 1, 2, 3 parallel lines here. If I'm focusing on these 2 line segments, though, if I know that those 3 lines are parallel, the same idea holds true. Think sides are being split. So AC over CE equals BD over DF, and that's the ratio that you can use. Now, the second type of theorem that we're going to see is called the angle bisector theorem, and just that is going on. An angle is being bisected. So if a ray bisects an angle of a triangle, it divides the opposite side into segments that are proportional to the adjacent side. So let me scroll up slightly here. So again, if you have a ray that bisects an angle, so AC is bisecting this angle right here. If that is the case, then the side opposite each of these, okay, so BC is proportional to the other opposite side, and then you're going to match it with the sides that are adjacent, which is AB and AD. So BC over CD equals AB over AD. If flipping back and forth is too confusing, then just do this. The side opposite over the matching side adjacent, so BC over AB, equals the side opposite over the side adjacent, which is AD. That might be a little bit easier to figure out. Okay, but it's the side opposite and the side adjacent. Those are going to be proportional to each other. All right, next one. It says BE is parallel to CD. Have that. And I have these 4 numbers written on here. So I have to find ED. Well, if I'm finding ED, that is a side of the triangle. B intersects the triangle, E intersects the triangle. So I'm going to use the side splitter theorem to help me figure this out. So again, the side is being split. So 4 over 2 equals 7 over ED, and I get ED to be equal to 3.5. Now, part B, though, right here is asking for CD. Well, the first thing you have to notice, though, is that CD is a base. The theorem is called the side splitter theorem. It's not called the base splitter theorem, which means you cannot use that theorem to solve for CD. So what we have to do is, just like I wrote right here, we have to use the fact that we have 2 triangles that are similar to each other. So the big triangle and the little triangle are similar. So here's our little guy. And then we have our big guy, which goes right here. And if you look at who matches up with who, the 6 matches up with CD, which we don't know, so we're good there. And then the 7 and ED, that's fine, but let's use what we already are given just in case we made a mistake on A. So 4 is good for the blue triangle, but you can't use 2 because 2 is only the side of that bottom trapezoid. So you actually have to add up both of them. And then you're going to use 6 for the side of the actual big triangle itself. So you can do 4 over 6 equals 6 over CD. And you end up with CD equaling 9, or another variation of that same type of proportion for that. All right, with the next example, we've got 4 lines that are parallel to each other. 1, 2, 3, and 4, and we're asked to find KM. Well, first thing we notice is we have a ratio of 5 to 2 to 8, so I'm going to just add some x's here. If I add them up, I get 24 of them. Or I know, sorry, they equal 24 in total. So what I want to figure out is, okay, well, what is my missing values here? So x comes out to being 8/5 when I solve that side. So if I do 5 times 5/5, I'm going to end up with being 8. Okay, so, and again, KP over here, that was equal to 24. That was given to us. Okay, so you also, the other option that you can do, because that might have been a little confusing with the ratios, is we're looking for KM, so I'm going to give that an X right here. I know that this full entire segment right here is equal to 24. I know that this full segment is not 24, it's actually 15. So I think the easier way of doing this would be 5, because that's the side that matches with the KM. So you can do FG over FJ, which is the whole thing, equals on the other side KM over the whole thing, which is KP. So FG is 5, FJ is 15, KM we don't know, that's my X, and KP is 24. And when you cross multiply and divide, you're also going to find out that you end up with 8 for that final answer. I think the proportion way is a lot easier. I'm actually going to scratch this way. The proportion is a lot easier for that one. All right, so let me show you this one here. So it says we've got RVS is congruent to SVT. So when you see that, the first thing you ask yourself is, okay, what's going on? Well, this segment is splitting that angle. So it is an angle bisector. So if it is an angle bisector, remember, it says that the side opposite and the side proportional, or the side adjacent, are congruent to, or proportional to each other. So opposite one of the angles that's congruent is 4. On the same side adjacent to that would be 8. And then I do the same thing on the other side. The side opposite is x. The side adjacent on the same side is 10. And when I cross multiply and divide, I end up with x, or ST, equaling 5 for that. All right, we got 2 proofs here, just to show you how these theorems are used in proofs. All right, first one. We've got 2 things that are parallel. So this guy is parallel to this guy. We know XAY right here is congruent to XYA. So we got a nice isosceles triangle, and we're trying to prove this proportion. So XA parallel YZ. Angle XAY is congruent XYA. That's given. So I know 2 things are parallel, which means I can use the side splitter theorem, which says that WX over XY equals WA over AZ. Well, also looking at this triangle right here, if those 2 angles are the same, I know that the sides opposite have to be the same. So that's my converse isosceles triangle theorem. Then, based on the information that I have, if you look at this proportion which you're trying to prove, and then the one we wrote in 2, everything is the same except these 2 things. But in line 3, we just said that they were equal to each other. So I'm going to replace one with the other, which is the one I need for my proof statement, and I'm going to use substitution to finish the proof. All right, final proof down here. So now we have a double situation. We have 2 sets of things that are parallel. So we've got this guy is parallel to here, and this guy right here is parallel to here. So first thing I'm going to use, again, sides are being split, I'm going to use the side splitter theorem. And because I have 2 scenarios, I'm going to get 2 proportions. So again, variation on how you write the proportion. There is no one right way. So CD